let's start our next lecture. It's a pleasure to introduce Phiala Shanahan from MIT. And her first lecture is Lattice Field Theories with Fermions, Part 1.
Okay, thank you very much. It's great to be here. So, okay, so I know you've already had an introduction to lattice field theory from Mike Tepper, so we're not going to rehash most of that. We will get a little bit into the weeds over the next 2 lectures, which are on this topic, so today and tomorrow. But what I really want to hopefully leave you with is a sense for if you want to do some sort of a lattice field theory calculation of a theory with fermions, why you need to think about the discretization of the fermions, where that gets nasty, and ultimately sort of what's easy and what's hard in lattice field theory. I know there's some people who do lattice field theory here, but I think most of you don't. And so the sense I want to leave you with is really a sort of feeling for what lattice can do, what it can't do, and where things get nasty, right? Okay, so just a reminder, lattice field theory just is a quantum field theory defined with a space-time lattice regulator, right? It's a definition of the field theory. And so what that means is that you really have a different but equally valid way of defining your field theory as a dimensionally regulated quantum field theory, right? It's a different definition, and so some things are easier and some things are harder to compute in this framework, right? So an example of easier would be the fact that you can do non-perturbative calculations quite straightforwardly in the lattice prescription. An example of harder would be Lorentz symmetry. Anyone want to guess why Lorentz symmetry is something hard on the lattice side? Yeah. Yeah, that's part of it. Any other ideas? Sorry, I like to talk, otherwise I feel like I'm lecturing to avoid back in Zoom times. Yeah.
Symmetry is harder to see.
Yeah, exactly. That's the part I was getting at. When you break down to a hypercubic lattice, you've broken your Lorentz covariance, right? And so you have to get it back in the continuum limit, but you have to be careful about how you do that and how you get it back. And so you have a definition that works fine, but you need to be careful in some cases, and that's just one example. Chiral symmetry will be another example. Symmetries in general are things you need to be careful about. Okay, so different but equally good. DRQFT, dimensionally regulated quantum field theory, right? Just a different regulator. And as I said, it makes your life easy in some ways and hard in some ways. So one example of the harder was that the lattice breaks your Lorentz covariance. And you can get it back, but you need to be careful. However, it's valid for all coupling strengths. Okay, so this is the setup. If you do a lattice field theory calculation, right, the very first thing you need to do is say, Well, what's the physical thing that I want to calculate? That's step one, right? And as you've known from your introduction to lattice field theory lectures, what you can access are expectation values of some sort of operators, right? So step one is relate whatever the physical thing is that you want to some correlation function. That might be easy or it might be hard. There might be a very obvious correlation function that directly gives you what you want. There might not be. You might only be able to access the physical observable you want in the limit of some series of correlation functions defined in some effective field theory framework, right? You might need to invent something new. But either way, you need to say, what is the correlation function? That's step one. So, oh, heavy boards. Okay. I need the stick. Okay, so what we want is, of course, study some physical quantity. Right? And number one is figure out what correlation function you need to compute that will give you P. So okay, so as I said, there might be multiple options. You might need to invent a new one, construct something highly non-trivial. At this point, you also really need to think about what the precision goals of the calculation are. It might seem counterintuitive that you have to do that right up front before we've even talked about putting your field theory on the lattice. But how you go about putting the theory on the lattice can depend on your precision goals, right? If you're willing to compromise some symmetry because you know the effects will be at the percent level, but you only care about your answer to 10% precision, maybe that's a much more efficient way to go. If you want something at fraction of percent precision and you know your physical observable really cares about some symmetry, you better get that in really precisely, right? So at this point, you also want to understand precision goals. Okay, then step two is what we're really going to be talking about for the next couple of lectures. And that is you need to define the discretization of the action of your theory. Right, you're just starting with some theory that you've written down in the continuum. You have to figure out how you're going to put that into a lattice discretization. And so this is what we'll really come back to after we finish this little introduction. And in particular, what to do about fermion discretizations, right? So ideally, you might be thinking, surely any discretization will do, right? And in principle, that's true, but in practice, it can really matter. So especially the symmetries of the action. So just one example of that is maybe chiral symmetry protects you from some operator mixing, right? And then if you break chiral symmetry in your discretization, you have to be really careful about what you're going to do with that operator mixing. You have to remove it somehow. And in some cases, that operator mixing can be power divergent in the lattice spacing, which means as you take the continuum limit and make the lattice spacing smaller, the mixing gets worse and worse and worse and worse. So though in principle, you can take that limit and get rid of the mixing, in practice, it might be numerically unfeasible, right? So these are the types of things you need to think about at this point. And so in that case, if chiral symmetry is what's protecting you, maybe you need a chiral fermion definition, right? Maybe chiral symmetry doesn't matter for the operators you care about, then maybe you choose to break it. All right, so that's really what we'll come back to. But just to finish the thought, step 3 would be you have to define the parameter sets for your calculation. and how to tune them. Okay, so by that I mean you need to decide on. Okay, so part of the premise set would be the action. The parameters of the action. What else might I have to define before I start doing a calculation?
Number of sites.
Yeah, the lattice geometry. Anything else?
Age group.
Yeah, I'm saying that's part of the action, but yes. You also have to decide what sort of statistics you're going to accumulate, right? And how many different parameter sets you're going to do. So, okay, and how you decide on these sets is you need to define them so that you can reach all the necessary limits you want to take. Continuum limit, infinite volume limit, depending on what you're getting at. Right, so ultimately you never do a single lattice field theory calculation, right? You do a series of calculations with finer and finer lattice spacings, bigger and bigger boxes. Maybe you change the quark masses or the masses of whatever fields you're in your theory, and you extrapolate and interpolate to get the results you're interested in. And you have to make sure that everything falls out correctly in all of those limits. Okay. I also said, but I didn't write, you also have to decide how you tune the parameter sets. So what sets the physical scale of the lattice spacing in a lattice field theory? Does that come out of the calculation, or do you have to set it somehow?
On the QCD.
Second.
Lightest particle.
Size of the lattice, what, sorry, what did you say?
Is the lightest particle.
The lattice size is correlation length. How do you even know? So if you're going to set the quark masses, you're going to put in some bare parameters and you'll calculate something. And what will come out, I think you talked about, computing masses in the last lecture. What will come out is the lattice spacing times your mass that'll be something dimensionless. How do I turn it into something dimensionful? Yeah, you have to measure in nature, right? You have to set what you mean by matching to something in nature. You have to set all your bare parameters like quark masses. You also need to set the lattice scale that requires one additional input. And so if you're doing QCD, you go to experiments, you measure some hadron masses, you measure the omega baryon mass as something that doesn't depend strongly on the light quark masses, and use it to set the scale. But if you're not doing QCD, if you're doing a theory where you can't go measure something experimentally, you need to define what you mean, right? Then there's a definition that comes in at this point. Okay. For choose algorithms, run calculations. Okay, and 5 is do the statistical analysis. At each parameter set, and then extrapolate, interpolate, interpret. That was interpolate, and this was interpret to get P, right? So that's it. The big one here for us is really number 2, which is, well, how do you put a theory with fermions onto a lattice discretization without messing it up too much, right? Any questions before we go there? You can think while I move the board, since I think that's going to be an event. Okay. Do you want to come up with questions? Yeah.
If you start from arbitrary lattice models, can you just tell what kind of continuum theories it should be when you go to the continuum limits?
You mean, can you start from some discretization of the theory and look at the continuum limit?
Well, maybe you don't know
Yeah, you can start from some lattice discretization and look at what it gives you in the continuum limit. Yeah, that direction's sort of easier, usually. Okay, so fermions. What sort of fields are fermions? Yep. What else? Yeah, they anti-commute, right? So we have fermions into the path integral as Grassmann valued spinor fields. Okay, so we have this, right? Anti-commuting, spinor indices, spatial indices, right? Okay. So let's start with a continuum action for a single free Dirac fermion, right? Okay. Okay, why are both my mu's downstairs? I'm in Euclidean space now, right? That's also why there might be i's missing or signs different from what you might have in your mind, right? This is my Euclidean action. So these are Euclidean Dirac matrices. Right, okay. We've got our single free Dirac fermion and we want to compute some sort of correlation function, right? And so I'm going to take a partition function. I'm going to take external Grassmann sources and I'll do everything we usually do, right? So let's just write that down. Partition function or generating functional, if you like. Okay, because the board's short, I'm being a little sloppy, right? This psi bar m psi is actually this whole integral here. And similarly, these eta psi's, this is really the integral of dx, eta x, psi bar x, right? We're just compactifying onto the board. All right, if we change the variables, we can actually integrate out all of the fermions explicitly. It's really useful. Let's send psi prime and psi bar prime. Right, and I'm just going to make these substitutions. Okay, so this is exactly the same as that. I've just substituted in And now I have psi prime variables here instead of the psi variables I had before. The reason for this substitution is that now the psi primes only appear here, and this is beautiful and quadratic, right? So I can just do the Gaussian integral. Gaussian integrals over Grassmann variables. This is just going to pull out a determinant. You might be more used to seeing like 2 pi's over square roots of determinants. In the Grassmann case, it just gives us the determinant here of this matrix. So this is just okay. So that is really nice. We've just done the integral over all of the fermion degrees of freedom exactly, which is why when you're doing lattice field theory calculation, as we'll summarize again in a minute, when you do the sampling to do the Monte Carlo integration, you're only sampling over the gauge degrees of freedom because you've already integrated out the fermion parts. But okay, so this is our generating functional. We can write down what correlation functions look like. Right. Right. This just looks like it always does. We're differentiating with our auxiliary fields. Right, just our usual correlation function from the generating functional. Okay, but we know what these derivatives look like here, right? Those are really easy when all we have is that quadratic looking exponential. So we have this is just going to pull down that M inverse, right? So this looks like right? So really just the M inverse, the exponential, and then terms we don't care about. So what that means is that this correlation function here, it just looks like a bunch of these inverses of M. That's just the Dirac matrix, right? It's just a bunch of propagators tied together. So what you do setting up the lattice field theory calculation, you integrate out the fermions, you write your expectation value of your observable in terms of propagators, and then you have to do the gauge part by Monte Carlo sampling. And on each sample of all the gauge fields, you calculate your propagators by doing Dirac matrix inversions, and you tie them all together. Okay, I'm just going to write down this substituted in here. Maybe we can do it on the shortboards, but feel free to ask questions while I rearrange. Yeah, let's hold that thought until we've looked at discretizations, because part of your question will be answered. Ask it again if a little later once we've started talking about discretizing the action. Okay.
For practical purposes, is it necessary to choose some convenient representation of the gap analysis or?
Right, so we haven't even discretized the theory yet. So once we discretize it, these guys are going to be big order volume times order volume matrices, where volume I mean the number of lattice sites. And so really the spatial degrees of freedom are really the overwhelming part here. But sometimes if you choose a nice representation, you can get away with not inverting the whole thing. And so sometimes, you know, if you're really going for high precision and saving a factor of a little bit helps you, yes, it can be useful to choose other representations that you might not otherwise choose. But the volume factors are really what is going to dominate here in the numerical inversions. Okay, let's just finish this thought on correlation functions. So this guy, we'll call this y. Is just going to look like some bunch of inverses. Tied together. And so in a lattice calculation, you compute the fermion propagators, you can track them in all ways, and then you integrate over the gauge degrees of freedom. So you can already sort of see just by looking at this where the computational costs come in lattice field theory calculation. One is you're going to have to integrate over the gauge degrees of freedom by Monte Carlo because we can't do that explicitly. So you're going to have to sample the gauge fields. That's expensive. Two, on each gauge field, you have to compute these guys. As I just sort of hinted at, these end up being really big order lattice volume squared dimension matrices that get closer and closer to being singular as you make the quark masses lighter because of that m, right? So that gets numerically harder and harder. That's why historically a lot of lattice calculations were done with heavier than physical values of the quark masses. I was thinking, 15 years ago, just because of computational cost. And then once you have them, you have to tie them all up. The contractions usually aren't super expensive unless you're doing something like nuclear physics, which is something I like to think about, where you have, factorially many propagators you have to tie up, and then the contractions can get really nasty also. All right. So this is the setup. Now we're going to talk about how to put your fermionic action on the lattice. Any questions about this general structure of a lattice calculation before we dive in? Okay, so I know you've already had hints about fermion doubling. We're going to see in a little bit of gory detail why just doing the most naive thing isn't necessarily what you want to do. Okay, so let's start with, our Euclidean Dirac action, free fermion. We had it before, but I'll write it again so it doesn't get wiped off. Narrow boards. Okay, we're going to discretize the theory onto a four-dimensional hypercubic lattice. You could choose other discretizations. This is just the easiest one to think about for now. In general, simpler discretizations are better because the more you break your symmetries, the more you induce mixing between operators that don't normally mix, some of which, especially if the mixing is with lower dimensional operators, will be power divergent as you make the lattice spacing small, which is really bad, right? So getting too fancy with your discretization usually hurts, but is sometimes useful. So discretize the theory. The other reason people don't play around too, or some people play around, but the other reason most calculations are done with sort of a simple discretization is that the sampling step of making these configurations are so expensive that we share them internationally for different physics calculations. So if you have a discretization that's great for just one observable, you invest a huge amount of resources and then you can't go and use those samples for other calculations also, right? So it's sort of combined. This is usually a good choice, and it's a choice that works for many things type situation. Okay, so here's our lattice. most of what I talk about is not going to be specific to 4D. I'll put Ds for dimensions later, but just for now, let's think about 4D. Okay. Okay, I'm going to just define my sites on a lattice geometry. And I'm going to put the quark fields onto the sites of the lattice. So what used to be my field defined on all space-time is going to be defined just on the sites, right? We're discretizing, so dx becomes a sum. Now, path integral discretizes in the obvious way, etc. Right? So far, no surprises. But now let's think about that action up there. There's a derivative. How do you normally discretize derivatives? Finite differences, right? Let's think about what happens if we do that. Okay, I'm going to write down remember, we can only move by single lattice sites here. So this is a unit vector in the direction of mu hat. Yeah, right? Board rearrangement. Oh. I'm going to ask you what's wrong with that in just a sec. Okay, what's wrong with that? Yeah, it's not gauge invariant, right? That's bad, right? So gauge transformations of our fermion fields, they look like this. Remember? Where this omegas in whatever your gauge group is, we'll call it SU3, but right. So that discretization doesn't work. We can try to fix it up in the most naive way. What would be the most naive way of making something like that, this finite difference gauge invariant? Yeah, we need to do some parallel transporting, right? We have to just chuck some parallel transporters in between. We have very convenient parallel transporters. They're the gauge links that you've talked about a lot in the other series of lectures, right? Gauge links just are parallel transporters. So we can introduce them. Okay, so gauge links. Right, so I've just written the gauge length explicitly so you can see how it's a parallel transporter taking me from one site to another. So this n plus some parameter lambda times mu hat. When lambda is 0, this is at site n. When lambda is a, the lattice spacing, this is one site over. Right, so the gauge links really can be written out as parallel transporters. And the gauge transformation property is exactly what we need on one side we've got the gauge group element one site over, and the other one, the one on the original site, which is exactly what we need to fix up that, as I'll write on the next slide. So because they have this nice parallel transporting property, that's of course why we identify them on the edges of the lattice, because they live sort of between the two sites. They're on the links between the sites. Oops. Dear. Okay, that middle board is just going to be invisible for a while because logistics. I'll put it back at the top in a minute. Okay, so let's, so just a reminder of what I just said is, this is of course why we like to identify the gauge links on the edges of the lattice. Right, so this is n, and that one there is n plus mu hat. Mu hat's that way, mu hat's that way. Then this link here, right, that'll be u mu at n, which is the link sitting at n going in direction mu, right? And we'll have mu dagger at n. What would daggering the link at n do? Yeah, it's going to just turn it around, so that will be u minus mu at n plus mu hat, right? It's the link going in the opposite direction, sitting here, if you like. Okay, so since we have these parallel transporters, we can replace in the finite difference with this guy, where we've sandwiched in that parallel transporter. Remember, we had this inconvenient mismatch between our n and our n plus mu omegas in our original finite difference. And now this guy is just compensating for them. And so we have a nice gauge invariant action. Okay. So this, we'll call this our naive discretization. Doing a symmetric finite difference. That's why there's the 1/2a there. Okay, why do I have the a to the power 4 out the front? Yeah, just get the dimensions right. Right, I'm doing an integral over all those sites. If our sites have some sort of dimensionality that's carried by the lattice spacing, if the separation has some sort of dimensionality that's carried by the lattice spacing. Okay, so I'm also going to write this in the form we had before. Okay, so D, our Dirac matrix there, is now a matrix in what indices? I only have one set of indices explicit. It's in space-time indices. Those are the explicit ones. What are the indices I didn't write? It's a matrix in space-time, color, and Dirac indices. Right? I just wasn't very explicit about the color or Dirac indices. I'll be a little bit explicit about them now. I've now lost track of which of these boards was which. My apologies. We're just going to write on this one. And then I'll keep the new boards in the right order. Okay, so this is now some really big matrix. Your combined space-time sites, color, Dirac indices, you should be thinking about numbers like 10 to the 9, right? Maybe even a couple of orders of magnitude bigger, and that's on each side of this. So this is a really, really big matrix that we're going to have to invert to make the propagators. That's one of the big expenses of lattice QCD calculations especially. So this D is matrix in space-time, color, Dirac. So let's just be, for once, really, really explicit. We've got color, A and B, Dirac, alpha, beta. What indices does this guy have for being really explicit? Yep, alpha, beta. What about this guy? Yep, color indices. We need a delta function in the spatial indices. Okay, so far everything looks pretty good, right? We took our fermion action, we discretized it, we know how to integrate out the fermions, and we're going to end up with propagators, which mean inverting these really brutally large matrices, but everything looks good, except this has a really weird continuum limit. So this has a continuum limit where you have too many copies. We have doublers of all of the fermions. So this is a problem. Okay, and I want to show that a little bit explicitly because I think it helps give a little bit of intuition for the ways we try to solve it also. So let's think about the Fourier transform of the inverse of the free 2-point function, right? So the 2-point function looks like a propagator. Fourier transform is going to take us to momentum space, right? So I'm looking at something related to a momentum space propagator. So let's write down right? Why am I starting to look at propagators in momentum space, right? Because we know what propagators look like. We know where they have poles, and we're going to see that this thing has way too many poles corresponding to the different species of fermions. Okay, so what are K and L over there in my arguments? They're numbers, vectors. K and L. What sorts of objects are these guys? Yeah, these are four momenta, right? Discrete four momenta. So those have indices, right? These guys are lattice sites, which have, okay, 4 if we're in 4 dimensions, whatever our dimensionality is, right? Okay. We know what this is. We saw this before. This looks like D, right? We had it just over here, that our 2-point correlation function looked like M inverse. M is now D, and this is the inverse of that guy. So this just looks like the D we have. So this just looks like yeah, we're in Euclidean space. Okay, and I don't want to think about gauge fields, we're talking about fermions. So we're just going to set all the gauge links to 1 for a moment. Okay, so trivial gauge field. Now, how do I get that board back is the question of the moment. Okay, so let's just substitute in D. These sitting up there really explicitly. I can just put it in, right? So okay, all my brackets closed. Please, if I make a Bordeaux typo, just please shout out. Those delta functions, I can just apply them, right? Get them out of there. They let me get rid of one of these two sums because each of them is a delta function between m and n in some shift. What does this look like? I did the delta function over m, so I should be left with just n. Okay. What does the start of this expression, the bit with the ends in it, look like? What does the start of this expression, the bit where the ends are, the sum and that exponential, what does that look like? Can I write it in a simpler way? No ends anywhere here, so just this bit. Just looks like a delta function. Yeah, right? We're in discrete, so we've got the sum, but that's just a delta function. Why should we have known right from the start that we're going to have a delta function in K and L come out of this? Yeah, what? Yeah, you're saying the right thing. I sort of, these are momenta, so I wanted you to tell me a momentum conservation, but it's the same thing, right? So delta function because of momentum conservation, right? Right, and this guy is just my momentum space guy. Okay, where'd the sign come from? Yeah, right, I just wrote this as a sign. Okay, good. So now let's think about the inverse of this guy. Let's think about our momentum space propagator. And I want to think about where D inverse K is singular, right? Where should D inverse K be singular for a massless particle? Yeah, I mean, that's what we're going to see. But in the continuum theory, how many places is D inverse K singular? Okay, let's just write it out. No space. I'm just going to write the inverse of that. So we've got A plus IB. I'm going to multiply the numerator and denominator by A minus IB to make it look pretty. I'm just going to write the inverse of that. So if you want the position space propagating, just Fourier transform it again. Right, we're just looking at the momentum space propagator. And like I said, I just took 1 over that guy and multiplied the numerator and denominator by the same thing to make it look pretty. Okay, so let's set the mass to 0 for a moment. Okay, it's my Fourier transforms were wearing tildes, we'll put them on. Okay, this guy is singular at k mu is 0, right? That's what you expect for a massless particle. However, it's also singular at a whole bunch of other places, which is not what we want, not what we expect for a massless particle. Hopefully by the 3rd lecture, I'm going to get the hang of these boards a bit better. Sorry. Sorry, I can hear you're asking a question, but the boards are loud. Give me half a second. Yeah, yeah. So I didn't hear the end of that. You said again? Yeah, so you're right that you need to be careful about scales when you're doing your lattice discretization, and making momenta too large will be a problem. You have to take fine enough scales to be able to take large enough momenta, but this is a problem regardless. So what we have we'll do a Taylor expansion to see this in just a minute. What we have is so why this is a problem regardless, we'll in just a moment we're going to see this another way by seeing that you can understand all of these different singularities here as also being a symmetry of the action under a transformation, right? It'll be a symmetry of the action, which basically relates different copies of fermions that are all going to be indistinguishable physically, because you can understand it as being a symmetry of the action. Okay, but so it's also singular at all of these points, right? Just by plugging it in. If we like, we can index them by A. You can think about these all being in our first Boolean zone. If you have n sites, your minimum momentum, if you like, is 2 pi over n times the lattice sites, right? That's your minimum momentum. So then you have n momenta in our first Boolean zone. But regardless, we have here 2 to the d, which in the case of 4D is 16 points where you have for this this propagator up there where you have an approximately linear dispersion relation, right? So we have 16 copies of the fermions where we wanted 1. We were trying to write down a single free Dirac fermion. We have 16 copies of our Dirac fermions. So okay. Another way of seeing that, like I said, we can think about symmetry transformations, and let me sketch an example of that. Oh, clearly my stick craft is bad. I lost my stick. You still have problems. You're sort of almost hitting on one of the ways we might try to deal with this, which is to add something extra to the action, which pushes a bunch of the masses up and out of the way to make them irrelevantly large. So that would be one example of getting rid of fermion doublers, or getting rid of, for practical purposes, fermion doublers is basically to play with where they sit in the spectrum. But there are other ways too. We'll write down a symmetry transformation right now. Okay, so let's think about being near any of those k's on the other slide and taking a naive a goes to 0 limit. So I'm going to think about taking some momentum that looks like this, right? So I'm just going to take our k mu a with some small shift. Let's not take the massless limit here. Let's keep the mass. Okay, add a sine. Why have I got a cosine now? So I'm just Taylor expanding here, right? So what I'm doing here is I'm taking sine k mu a. This guy is this plus some p, right? And I'm Taylor expanding for small p. So this looks like sine k mu a plus a b mu cos a k mu a. Right. I'm sorry, can you say that again? This is D inverse. It's for what? This D inverse here is just that guy defined for any k I like, but then I'm being near k mu a plus a shift and then I'm Taylor expanding for a small shift. So this line here is just for the Taylor expansion for K near K mu A, right? I've just taken that expression at the top of that board there. I've made this substitution, and then I've Taylor expanded for a small shift. So this is just the Taylor expansion of that sign. We get the sine K mu A that vanishes, plus AP mu times the cosine. That's why we're left with the cosine here. Okay. I don't have anything in the denominator, and that's because this cosine here, for all of the K mu A's, this is just plus or minus 1. Right? And in the denominator, we'd have a cosine squared, which is just 1. Right? So this is just plus or minus 1. Okay. So for each of our copies, the only difference is the sign of that term there. For each of these 16 or 2 to the d, a different number of dimensions, fermion copies. Okay, so this cosine so let's write down a set of unitary matrices which will transform between these different copies. So let's define, remember A is the thing indexing my 2 to the d copies, just like on the far right hand board there. If I write down this set, and you can check this. Okay, these S's are just I, gamma, rho, gamma 5, where this index here is the index of rho. So each of these is just finding some matrix that's a product of a bunch of gamma matrices, right? Then we can relate these different near zero energy regions like this. Up to discretization artifacts. You can also do this to the action. You can think that this is if we call these different copies different tastes, you have a taste exchange symmetry of the action. To symmetry of the action, it means that these guys are physically indistinguishable. You can think what's really happening here is that this label A is basically acting as a number, as an extra quantum number that's specifying the taste of the fermion. Right? So here I didn't write the action, I just wrote it for this propagator, but you can see that the left and right multiply, this unitary transformation on the propagators is moving between these different near zero energy regions. Yeah. Well, we just have these 16 discrete, or 2 to the d discrete copies. I'm going to gauge that symmetry. That's interesting. I haven't thought about that. Sorry, did someone else say something? Yeah. Then you're going to get a different theory, but okay. From this, actually, you can sort of straightforwardly see a relation between what's going on here and why this is messing up your chiral symmetry. So we have a relationship. Okay, I'm giving up on that hidden board. We have a relationship between our fermion doubling or copying problem and chiral symmetry in our theory, which we can see, at least we can get some intuition for pretty easily. So okay, so let's think about just a naive action for left and right-handed fermions, massless limit, right? So I can write this propagator just with some projectors. All right, so let's think about okay, so let's write we're just taking exactly the form that we had over there. Now I'm taking the massless limit. Okay, just a projector. Get the left and right-handed pieces. Let's pop that projector inside. We're just going to commute it through with this guy, which is just a product of gamma matrices. All right. Okay, so this epsilon, that's just a sign that's coming from commuting through all my different gamma matrices. And what you find is that regardless of whether I started with the left or right-handed guy, I'm going to end up with 8 combinations which have a plus sign and 8 combinations with the opposite. So I had 16 doubler modes. I tried to write down just a left-handed fermion, and I actually have 8 left-handed and 8 right-handed, right? So basically we've failed to separate the left and right-handed pieces. Okay, so trying to naively project out didn't work. So there's a more general statement of this, which is that if we write down any fermion action that's translationally invariant, local, and Hermitian, the action is going to have an equal number of left and right-handed modes. Huh? Yeah, and I'm also going to write it down. Is that what I said was a bunch of general conditions, you're going to have an equal number of left and right-handed modes. That's itself. Is this the first board I've written on in the new round? Yeah, thanks. Okay, so let's think about some general action. Okay, so I'm trying to project it, right? I want something left or right-handed. I'm going to say I have a bunch of general properties, so it's going to be translationally invariant. So F, M, N is only going to depend on the difference between M and N. It's going to be local. What I really want is that the Fourier transform is smooth, right? It's going to be Hermitian. What I really want there is that the Fourier transform is real, right? Then we have a general theorem. This is a special case of the Nielsen-Ninomiya theorem. Tells us that the action corresponds to an equal number of left-handed, right-handed modes at low energy. Okay, so we sort of looked at a very special case where we got an equal number of left and right-handed modes, but this is a generic statement for any action with these properties. So we can't write an action for a single chiral fermion, right? It's, whoa, okay, thank you. Okay, so another way of saying this, which is, it's really much more general, and it's a more general theorem than just the Euclidean case also. Let me just reword this theorem. So, oh dear, that goes to the chalk gods. Okay, reworded more generally, it is not possible to construct a lattice fermion action that is ultra-local, chirally symmetric, undoubled, with the correct continuum limit. Okay. We have 5 minutes, so we do not have time to prove even a special case of this, unfortunately. And we also don't have time to go too much into the weeds. I was hoping to talk about staggered fermions, which is one way around this today, but let's talk a little bit more generally. If you want to try to prove this for the special case we looked at the easy way, you can basically reduce it to applying the Poincaré-Hopf theorem if you want to do a lecture exercise. It's not too bad, actually. Okay. So this is sort of bad, right? It means we need to try to get around it. And the ways to get around it, the general idea is that you have to violate one of these properties that we'd really like to have, and then try to make it so that that violation goes away in all the limits you want to take, right? And they all have various consequences for especially your chiral symmetry. That's a particularly key one. So Wilson fermions, which is pretty popular because they're nice and cheap, would be to break chiral symmetry explicitly, even when m equals 0, even massless. You break it explicitly, and then you add an extra derivative term to the action that acts like a large mass that pushes all the doublers up and out of the way. So it puts them to higher energies, and you put a coefficient on that term so that it vanishes in the continuum limit, and so everything should be okay again. So you basically move the doublers out of the way. It comes at the cost of extra discretization errors, which you then have to deal with. Another example that I'd hoped to talk about today was staggered fermions. You basically distribute the components of the Dirac spinner onto different lattice sites. And then you can see that you have a nice symmetry between these different tastes. We just saw that you have symmetries between the different tastes, but in such a way that you can remove a factor of 2 to the d over 2. So in 4 dimensions, that's a factor of 4 of the species. And then you're just left with 4. 4 is still too many, that's bad. To get back to 1, you can take a rooted version, then you break locality in a really sort of hideous way. So then again, you're breaking something and then trying to fix it up again, right? Tomorrow, we'll talk about some more ways of trying to preserve some of your chiral symmetry, or preserve at least a lattice version of your chiral symmetry, right? So this would be things like Ginzburg-Wilson fermions, where you write down a lattice version of your chiral symmetry that reduces to the chiral symmetry you actually want in the continuum limit. But okay, the problem there is that they're computationally more expensive. And so this means you have to make a choice of how to deal with this problem. And which choice you make really depends on what physics you're trying to do. Some have more discretization artifacts, some are really expensive. And so that balance takes us back to point 2 right at the start of when you're setting up the lattice calculation, what you have to think about. And this is really one of the big things you have to think about. So let me just summarize everything I said with various ways around the problem. Oh, sorry. Various ways around the doubling problem. And the general idea is to violate one assumption and hope the violation, or make sure the violation disappears in the continuum limit. Okay, and more tomorrow. Thanks.
Thank you so much for illuminating lecture. We have a couple of minutes for questions. Yes.
That's a very nice question, but I was wondering why the singularities are a real problem, because these are artifacts of the UV regulator. At least the pools in the continuum limit would appear at some very large values of k square at infinity. So from the effective filtering point of view, why would they matter at all?
Yeah, so I feel like you're wanting to do Wilson fermions. You're wanting to just move the doublers out of the way so they don't matter.
I see.
And
Just remove them from the
that is one option, is push them out to larger masses where they're not going to interfere with anything, right? But unless you do that, you've got a problem. The first is a special case. The second is a slightly more general rewording. The actual theorem is even slightly more general, not just for Euclidean space. But this statement is sort of the most general that we care about in this context. Yeah. Yeah. You can keep the extra taster rounds if you want. I mean, well, I mean, they're tastes here, flavors, but. Yeah, if you want this many flavors, you're good, right? But that's. Yeah. So I can't really hear you from here. Maybe you can either shout or come here and ask me, or you can ask me afterwards. Yeah, so this statement here that you can't construct a lattice fermion with all of these features is true under these general conditions, right? Your doubles won't necessarily look exactly like this, but you still have the scenario that you can't have ultra local, undoubled, right chiral limit, chirally symmetric. We didn't show it, but that's generally true. How so? Yeah. Yeah. I mean, this is true. You've given up on chiral symmetry to a much higher extent than some of the other options we'll talk about tomorrow. It depends whether that's important for the quantity you're trying to calculate, right? But you're right. In some sense, the discretization errors are the least offensive part because you can do semantic improvement. You can add lots of other pieces to your action tuned exactly so they cancel off the leading discretization effects. And it gets more expensive, but you can sort of deal with it. But yeah, yeah, that's the way of summarizing it.
Yes, suppose you adopt the Hamiltonian approach to lattice theory with continuous time. Does it reduce the doubling somewhat?
Naively?
For example,
I don't think so.
Because you can do the intermodal with one flavor. Staggered.
Yeah, so I mean, staggered reduces the doubling problem, right? By a factor of.
But I thought Euclidean 2D would still give you two flavors, but the Hamiltonian.
Yeah, it doesn't fully solve the problem though.
At least you can do one flavor.
But wait, you're in 2 dimensions? Okay, in 2 dimensions, yeah, yes. Sorry, can you say that again?
It doesn't look obvious that you are forced to.
I'm missing a key word there. Do the what computation? Off shell. Oh, yeah. So interpretation becomes the key piece of the puzzle there then, but. Yeah. Yeah, right.
All right. Well, thank Phiala again.